First of all, I would like to thank our organizing committee for this nice opportunity to present my little wishes onto you all. I'm Basanta Pt1 and I'm associated with Kathmandu University, and Mr. Brajesh Adhikari is also associated with Kathmandu University. So I'm going to present about wind energy grid integration and its impact in Nepal, which is a case study done for Nepal, which is basically done for grid integration impact analysis for wind power generator, which would be connected to the grid. And this is focused to voltage stability assessment. And this is the one result from SWERA project, which was done under AEPC. And this is the wind map that reaches, and those allowed figures given here is the wind-prone zone in Nepal, which is near 15 kilometers from NEA grid around the Nepal. And this is the overall value from that map itself. So by considering the commercially viable wind power density of 300 watt per meter square for 6074 square kilometer on that prone zone, we have wind potential in Nepal is around 3000 megawatt. So this research is basically done to find out the feasibility of that wind power while integrating to the grid. That means to know the penetration level of wind power in Nepal's grid. And this data is from reference 6, that is SWERA project, which is done under AEPC in Nepal. So main objective of this research is to conduct a voltage stability analysis using an iterative power system simulation package to evaluate the impact of strategically placed wind generator on transmission system with respect to the critical voltage variation and collapse margin. So that is basically a voltage stability assessment while integrating the wind generator in the grid in Nepal. So main theme or objective for this research is to study the technical impacts in the IPS, that is integrated Nepal power system, due to probable wind power integration in identified wind energy available site in Nepal, as cited by SWERA project. So this is the second assessment done after SWERA project. So impacts of wind turbine grid integration, from theory it says that after the operation and performance affect the operation and performance of the network depending on the scheme and rating of the generator itself. So these are power flow, wind power dispatch, voltage stability, power quality, and fault analysis. And this research is basically focused on voltage stability assessment. So these are the tools for this project. The first tool is PSAT 2.1.4. This is developed by the Professor Federico Milano from Italy during his PhD research. So I have used that tool to analyze the grid impact analysis for Nepal. That consists of the static load flow analysis with wind power in it, and continuation power flow analysis, which involves PV curve analysis. So this is the PV curve. So PV curve is the plot between transmitted power versus receiving in voltage. From this we can evaluate the collapse margin of the system and critical voltage point. So by analyzing the critical voltage point from the grid after wind energy integration to it, we can know the penetration level of the system. That is one aspect. So these are the key assumptions for this research. For Kathmandu Valley, Mustang, Pt1, Palpa, Butol, Ramecha, Pokalunga, these are the Nepalese wind site as cited by SWERA project. So I have considered these sites for the wind-prone zone for wind generator grid integration. And this penetration study was carried by voltage stability point of view. And for this case, generation and load data up to 2009 was taken into account, which were obtained from NEA, Nepal Electricity Authority, and simulation was carried out in PSAT 2.1.4. So I should thank Professor Federico Milano for his contribution in that PSAT. Otherwise, it could be difficult for me to simulate. This is the load flow analysis. So this is the network developed for Nepal. This is the Nepalese grid. which is owned by NEA, Nepal Electricity Authority. This is simulated in PSAT, and this is without wind generator integration in it. So this is for base case analysis without wind. So after analyzing this base case study, then from this network, we have selected 5 different wind corridor, network corridor for those wind prone sites. So, and from that network, this is the summary of that load flow. So in this network, buses were 77, lines were 108, transformer 15, all this. So in this network, we have a real power, total generation is 770, and reactive power is 240 here, and the load is 739. But in actual case, we have a more load than the generator. But in this analysis, all those losses and other things were supplied by the slack bus. So it is seen that generation is more. But at present scenario, we have more than 812 megawatt in our system demand in our network. So we have more than 180 megawatt deficit, power deficit in network, which is managed by load setting. So hope we can supply those power by this is now many penetration level assessment for INPS, and those were the corridors taken into account: Kathmandu Valley, Kagbeni and Thini, Yuthan, Palpa, Bujol, Ramechhap and Okaluna. Those are 5 corridors. And for those 5 corridors, 5 different transmission networks from INPS were selected, were designed for these wind penetration level. To select the different network from those INPS, all lines were truncated from there, and for these different networks, truncated part were replaced by PTCS generator or load as seen from the base case analysis. And power flow and PP curve was done in that software. So for Kathmandu Valley, probable PCC point of common couple, those were the name of substation, existing substation in Kathmandu Valley, which were taken from their physical locations near for the wind site around the Kathmandu Valley. These are existing substation. So this is the network designed for Kathmandu Valley for wind grid integration. So from 5 point wind was penetrated, wind generator were penetrated. So for this case, each turbine were considered for 1500 kilowatt, and continuous penetration was done. On the basis of continuous penetration to the wind power to this network, voltage stability assessment and voltage collapse margin was calculated. And this is the results for PP curve analysis. From there we can see the loading parameter for SHESH and loading parameter for 2 different cases for 2 megawatt and 12 megawatt. This is quite huge size, this is not a small scale. So from that we can see that after penetrating up to 12 megawatt, we can easily increase the loading parameter of the system from 1.4 to more than 2. So this shows that we can evacuate the wind power within Kathmandu Valley within existing network without much modification. This is the result which shows lambda max versus wind penetration and losses evaluation. So from the left figure it shows that the penetration up to 38 megawatt can be done in Kathmandu Valley without modification, because in the base case analysis is above 38 megawatt. If you go to 40 megawatt, then the lambda max will be less than the base case analysis. So we can go more than 38 megawatt in Kathmandu Valley. That means that we can evacuate maximum up to 38 megawatt wind power in Kathmandu Valley itself. And for that case, the loss tendency shows that within 3.27% of penetration, there is certain increase in the loss. This is because of the maximum wind generation penetration near the highly loaded line. So that has to be considered during practical evaluation. This is the network developed for Kagbeni and Mustang corridor, and for that case, single wind farm site was considered and wind penetration level assessment was carried out, and the result, well, this is the result for Kagbeni and Thini corridor, which shows that loading parameter is much more maximum, but it's less to 1.6 with a decrease up to 1.6 while penetration there. So we need some sort of change in that network. So this for this figure also shows that loading parameter is drastically decreased to less than 1.5. So this is not practically suitable for wind penetration in that site. And again, from this figure, we see that power system loss for the network is continuously increased up to 6.99%, while penetrating to 6.88%, there is loss more than 1.2%. So we cannot go for this. That's why this system is remodeled to get the highest penetration level in that corridor. So for that case, if we integrate the wind power to the far hill substation there in 11 kV voltage level, then we can penetrate more than 4500 kilowatt in that area in Kalbini and Thini network, Thini corridor, which means that we need separate transmission line to evacuate the wind power from that corridor in order to integrate to the grid. And the result for this shows that there is a little more stability of max loading parameter for that site with that type of modification. So it shows that we need some sort of extra transmission line to evacuate the power from that Kalbini and Thini corridor. So without added transmission line in that corridor, it's difficult for us to evacuate that power. This is the network designed for Okalunga corridor, because that is also one of the wind-prone site as cited by the Soira project. And after analyzing the wind penetration level for this network from voltage stability assessment, it shows that the loading parameter is almost stable within 1.4, while integrating from 0 megawatt to 8 megawatt of the wind power level. Now it shows that the lambda max is continuously increased. We can increase the system's loadability margin of the network up to 40 megawatt penetration in that corridor. So from this we can recommend that Okalunga site is from wind grid integration perspective, it is most suitable for us to penetrate, because we have a system loadability margin is continuously increased up to while penetrating 14 megawatt at that site. But from this side, the system loss is continuously decreased, but it is within tolerable region. From the figure, if we analyze that, it's within 3.98 to 4.06%, not that much less. So overall conclusion for those wind grid penetration analysis shows that within the Nepalese grid, we can evacuate 60 megawatt wind power without modifying any network constants or any network in existing INPS network. But apart from this, if we add the transmission network in Kalbini and Thini, we can even add more than 4500 kilowatt in the network. So with this, these are the references taken for this research. So with this, I would like to thank you all, and for this special thanks goes to these institutions and these people who are the key person and key institution to carry out this research. Thank you so much, and extraordinary thanks to you all.